Hello, we're going to do integration by partial fraction decomposition. This first video is going to explain integration by partial fractions, and it's going to go through a few examples. So to start with the intro, let's say I want to add these two fractions. First thing we would need to do is find a common denominator. Now our common denominator is going to be these two factors multiplied together, so x plus 2 times x minus 3. So to get that common denominator, I would need to multiply the first fraction by x minus 3 over x minus 3, and the second fraction by x plus 2 over x plus 2. So I can do that. My numerator is going to be 3 times quantity x minus 3 plus 4 times quantity x plus 2 all over our common denominator. If I simplify my numerator, let's do some distributing all over our denominator and combine like terms. And just so we can talk about partial fractions, let's multiply out our denominator. We get x squared minus x minus 6. Okay, so we should be able to go from our beginning to our end. What partial fractions is they give you an integral and they say integrate this, and note that u substitution wouldn't work. Our u, we would maybe try x squared minus x minus 6. That would make our du 2x minus 1 dx, and this is 7x minus 1. So u sub doesn't work. So partial fractions, we want to be able to go from this first fraction over on the right and be able to split it up into the two separate fractions, because we can integrate these two separate fractions. So that's what partial fraction decomposition is. So let's do this example. This is our first example. And let's just forget about the integration for a sec. We'll do that at the bottom. But let's talk about how do we go from this fraction on the right to the two fractions on the left. We want to be able to do this process backwards. So first thing we're going to do is we're going to say, I know, let's factor our denominator first. We have x minus 3 times x plus 2. So we're going to say, I know that this equals some constant over x minus 3 plus another constant over x plus 2. And you can use any letters you like, but typically we use A and B. So now I'm going to focus on this equation. And I want to solve for A and B. So first thing I want to do is get rid of my denominators. So to do that, I'm going to multiply both sides of the equation by x minus 3 times x plus 2. Okay, on the left side of the equal sign, the denominator cancels. We're left with 7x minus 1. On the right side, for my first fraction, the x minus 3's cancel. We're left with a times x plus 2. For the second fraction, my x plus 2's cancel. We're left with b times x minus 3. From here, there's a couple things you can do. I feel the easiest thing to do is strategically pick values of x to plug in that will help you isolate a or b. So for example, I'm going to let x equal negative 2. Notice when I do that, this first term is going to become 0, and then I'll be able to isolate b. So I'm going to let x equal negative 2. We get negative 14 minus 1 equals, the a term is 0, b times negative 2 minus 3. Negative 15 equals negative 5b, so b is 3. Okay, now let's strategically choose an x so that we can isolate a. I'm going to let x equal 3. Notice that if I plug in 3, that makes this term with b equal to 0. So we get 7 times 3, that's 21 minus 1, equals a times 3 plus 2. So 20 equals a times 5, and a equals 4. Okay, so now that we have a and b, I'm going to move this down, we can write out our final answer for splitting up this fraction. So we're going to say this equals 4 over x minus 3 plus 3 over x plus 2. And that is how we go from here to here. So now let's do this. Let's add in the calculus. Let's say I want to take the integral of this fraction. So if I'm doing this problem, first thing I'm going to do is I'm going to see if u sub would work. I'm going to notice it doesn't work. Maybe we could think about integration by parts. Also doesn't work. So I'm going to do partial fractions. So I want to factor the denominator. Oops, I changed my... Let's make this 7x minus 1, just so that we're all the same. So I'm going to factor my denominator. And then I'm going to do the partial fractions process. And we've already done that. So I'm going to say this equals what I got up here, 4 over x minus 3 plus 3 over x plus 2 dx. I'm going to split this into two separate integrals. All right, so from here, I'm going to do it in quite a few steps on this first example, just to make everything clear, hopefully. Okay, so I pulled out the 4 and the 3 because that doesn't help us integrate. For each of these, we're going to be doing u sub with the denominator equaling u. Notice that du equals dx in each case. So we don't need to introduce anything else into our integrals. Also, keep in mind that the integral of 1 over u du equals natural log of u plus c. So we're going to be using that property. So for the first one, I'm going to have 4 times the natural log of absolute value x minus 3 plus 3 natural log of the absolute value of x plus 2 plus c. We're just going to put 1 plus c at the end. And that is your answer for this first problem. I've got a few more examples for us to do. So let's move on to the second example. So same thing, we could think about u sub first. We would make u probably equal to our denominator. Du would be 2x plus 1 dx, and I don't have that in my numerator. So that means that we cannot use u sub. So we are going to be using partial fractions for this. So first thing we want to do is factor our denominator. So this is going to be x plus 2 times x minus 1. And I'm going to show my work for the partial fractions down below. I kind of like to do it on the side. So just like before, I'm going to say this equals some constant over x plus 2 plus some constant over x minus 1. So we know that a and b are both going to be constants. Let's go through our process. I want to get rid of the denominators. So I'm going to multiply both sides of the equation by x plus 2 times x minus 1. And we get 3x equals, on the right side, the first fraction, x plus 2's cancel. For the second fraction, x minus 1's cancel. And then we're going to strategically choose x's so that we can isolate a and b. So let's isolate a first. I'm going to let x equal -2. We get -6 equals a times -3. Notice when I plug in -2, this b term becomes 0. And that means that a equals -6 over -3, which is 2. Let's also now let's isolate b. I'm going to let x equal 1. So we're going to get 3 equals, notice your a term becomes 0. So we get b times 3. That means b equals 1. So that means that we have a is 2, so 2 over x plus 2, plus b is 1 over x minus 1. So now that we've done that, we can go back up, and I'm going to split this into two integrals. I'm going to have 2 over x plus 2 dx plus 1 over x minus 1 dx. And you can write out your u sub, or you can do it in your head. But notice that when we do our u sub, du equals dx for both of these. So we don't have anything extra that we need to put into our integrals. So we're going to get 2, pull the 2 out front, 2 natural log of the absolute value of x plus 2 plus natural log absolute value of x minus 1 plus c. And that is that example. Okay, let's do one that's a little bit different. All right, so for this one, I'm going to show my partial fractions at the bottom or below. And I'm going to factor the denominator. So we have a GCF of x squared. Now notice here, this is the same thing as x times x minus 2. So the rule is when you have a factor that's repeating, here the x is repeating, you're going to start with some constant over x plus you're going to increase your exponent until you get to what you have. So here we have x squared, so I have x to the 1. The second one is x squared, that's going to be some b, plus, and then x minus 2 is different, so we're going to have c over x minus 2. So when you have repeating factors, this is how we deal with it. We still have constants in our numerators, but for the denominator, you're going to increase your exponent until you get to the number of x's that you have. So let's do this example. Okay, so the process is the same. I want to get rid of my denominators, so I'm going to multiply both sides of the equation by x squared times x minus 2. So I get 3x squared plus 13x minus 10 equals, and this is going to be ax times x minus 2 plus b times x minus 2 plus cx squared. Okay, now let's strategically choose some x's, see what we can isolate. First one, I'm going to let x equal 0. That's going to isolate b for me. So on the left side of the equation, I get negative 10. On the right side, the a term and the c term cancel. So I get b times negative 2, which means b equals 5. I'm also going to let x equal 2. That is going to isolate the c term. So I'm going to get on the left side of the equation 3 times 4 plus 13 times 2, which is 26, minus 10, equals, my a term and my b term cancel, so I get c times 4. From there, let's see, I have 12 plus 26 minus 10 equals 4c. That's going to be 38 minus 10, which is 28, equals 4c. So we get c equals 7. Now, left over, we want to figure out what a equals, but if you think about it, there isn't really anything we can plug in to isolate a, so we need a different strategy. So for that strategy, I'm going to say let's start multiplying some stuff out. So if I start with this again, my equation, I'm going to distribute my ax and I'm going to distribute my b. We get ax squared minus 2ax plus bx minus 2b plus cx squared. And let's plug in for b and for c since we know those. I'm going to move my next example. Ax squared minus 2ax plus 5x minus 2 times b, that's 2 times 5, minus 10 plus 7x squared. Okay, so we have a couple options, but I'm going to group together on the right side of the equation. I'm just copying the left side. I'm going to group together my x squareds, my x's, and then I'm going to put my constant together. So I have ax squared plus 7x squared minus 2ax plus 5x minus 10. So I'm going to factor out my x squared from these two terms. I have a plus 7x squared, and then I have plus, I'm going to say negative 2a plus 5 times x minus 10. Now a couple things, I want you to choose what's easiest. But if we compare the left side to the right side of the equation, I have 3x squared and then I have a plus 7x squared. And the left side of the equation has to equal the right side. So I can say 3 has to equal a plus 7. And that's going to tell us that a equals negative 4. Another option would have been that you could have said I have 13x, that has to equal negative 2a plus 5. You should have gotten the same thing for a if you choose to equate those. But either way, we should get a equals negative 4. So now that we have that, we have all three. So a is negative 4, b is 5, c is 7. So I'm going to rewrite my integral . And let's finish our problem. So I'm going to split this into 3 separate integrals. Okay, so for the first integral and the last integral, we're going to use natural log. For the second integral, I'm going to bring my negative 4 out. For the second integral, I'm going to bring out the 5, but notice this is x to the negative 2 dx. So we're going to be using that basic power rule for integration. So I'm going to have, I don't need u sub for the first one, negative 4 natural log of the absolute value of x, plus 5, increase your exponent, and then multiply out front. So I'm going to make this positive and negative, plus 7. Notice when you do u sub for the last one, x minus 2. du equals dx, so we don't need to change anything. And we get natural log of x minus 2 plus c. I don't want to leave a negative exponent in my answer, so I'm going to rewrite it one more time. And there is our answer. Okay, we've got one more example. All right, let's do one more example. So for this one, again, I'm going to show my partial fraction decomposition below. This time, x plus 2 is repeated. So I'm going to have some a over x minus 3. And then just like we did before, I'm going to start with a constant over x plus 2 to the first power. And then I'm going to have another constant over x plus 2 to the second power. From here, I want to get rid of my denominators, so I'm going to multiply both sides of the equation by x minus 3 times x plus 2 squared. We get x squared equals a times x plus 2 squared, the x minus 3's cancel, plus b times one of the x plus 2's cancel, so I have x minus 3 times x plus 2, and then c times x minus 3, the x plus 2 squared cancels. So let's plug in stuff for x. Let's see what we can isolate. I'm going to start by letting x equal -2. That's going to help us isolate c. On the left side, -2 squared is 4. The a term cancels, the b term cancels. I get c times -5. So that means c is -4 over 5. It is okay to get a fraction as one of your constants. I'm also going to let x equal 3. That's going to help us isolate a. On the left side of the equation, 3 squared is 9. On the right side, my b term and my c term are canceling, so I get a times 3 plus 2 squared, so 5 squared. So that means 9 equals a times 25. A is 9 over 25. So same as the last example, I don't have a number I can plug in to isolate b. So I'm going to do what I did before. I'm going to plug in what I know. So I know a and before we equated the x squared terms, so let's just think about this. When I multiply this out, I'm going to get x squared plus 4x plus 4, and I have the 9 over 25 out front. So my x squared term is going to be 9 over 25 x squared, and I have x squared over on the left. When I multiply out the b term, I'm going to get b times x squared, and then minus x minus 6. So this is going to be plus bx squared. And these two sides need to equal because this is 1x squared on the left side. So just to make it a little bit easier for us, so if I factor out the x squared on the right, x squared is 9 over 25 plus b x squared, and this is a 1 in front of the x squared, so when I set up my equation, I'm going to say 1 has to equal 9 over 25 plus b. And this is 1 is 25 over 25, so b is going to be 16 over 25. And that is your b. So if I go back to my integral, this is going to be, my a was 9 over 25, b was 16 over 25, c was -4 over 5, and now we have this integral. I might move this down just so that we have more room. Okay, so I'm going to split this up. I'm going to bring my constants out front. And for the last one, I know I'm not going to be using that natural log property, so I'm going to write it as x plus 2 to the negative 2 dx. We are going to have to use u sub for all of these, but for all three of these, your du equals dx. So we don't need to change anything. So when I write out my answer, I have natural log of x minus 3 plus 16 over 25, natural log of x plus 2, minus 4 over 5. For this last integral, when I plug back in for u, I have x minus 2, increase your exponent, multiply by negative 1, so I have positive 4/5 plus c. And we do not want a negative exponent in our answer, so I'm going to rewrite it. And there is our answer. So those were a few examples of partial fraction decomposition with an explanation.